Okay, so the title of my talk here is Seeing the Quantum World, Electrons, Atoms, and Tunneling Microscopy. The thing that we do here at LCN is scanning tunneling microscopy, and this is some data that we published last year. So, when you do science, it might take you a month or a year or several years, and you do you study something, and then you analyze it, and then you write it up, and you write a paper that's probably like 4 pages long or something, and you submit it to a journal, and the journal sends it out to other academics who read it and decide if it should be published, or give you correct, give you suggestions for hey, you should modify it, and then they publish it. And you can also sometimes submit uh, um, an image for the cover. So we were selected for this journal to have our image on the cover of the journal, which is something that's sort of nice for us. And I'm going to come to the data that's on this slide. So I'll show you this, towards the end of the talk. Hopefully you'll be able to understand essentially what we have on this slide. I want to start by talking about length scales. So we're going to start from a meter, right, the length scale of a meter, and we're going to go down in powers of 10 down to 1 angstrom, or 0.1 nanometers, which is roughly the length scale of atoms, the size of individual atoms. So we start here at 1 meter. We have a guitar, but it's almost exactly a meter long. 10 times smaller, so the width of your hand is about 10 centimeters. 10 times smaller than that, we have coin. And 10 times smaller than that, we have a grain of sand. I think that's so that series kind of gives you a bit of a feel for this, right? So if you think like guitar, hand, coin, grain of sand. So that's the first 3 orders of magnitude decrease. Then at 100 microns, so the width of human hair is around 100 microns or so. Red blood cell, so now this is 10 times smaller, so 10 microns. 10 times smaller than that, we have bacteria, so the E. coli bacteria is around 2 nanometers in length. So if we go down another 10 times, then we have our favorite guy here, the coronavirus, 10 times smaller than that. And now we're at this device here. This is a FinFET. It's a fin because it looks like a fin, and FET means field effect transistor. And so I'm sure you all have an iPhone or similar in your pocket, and you have about 25 billion of those right now in your pocket. And what you did there, so from the little dots you're seeing here, these really are the atoms. But this is a different type of microscopy that I'm going to be talking about. So here they're kind of shining electrons through the material. So this is sort of ordered crystalline material. Then you have maybe some kind of an oxide, and then a more amorphous material around the outside. And electrons pass through these, and we can apply voltages to switch the currents on and off. And you assemble 25 billion of those into a space, like this, put it inside a phone, and then that's how they work. 10 times smaller. So now we have sort of small molecules. I've chosen here this molecule indigo. So probably you've seen these diagrams. So the idea here is that each one of the apices of the lines is a carbon atom, and then elements that are not carbon are drawn on explicitly. So the nitrogen, hydrogen, and oxygens here. This molecule is indigo. Humans have been using this molecule for 6,000 years or so. Anybody wearing jeans? So this is the thing that makes your jeans blue. And I forget, you have about 10 to the power of 22 such molecules in average pair of jeans. And underneath it, right, so that's the molecule, and then this is an image of one molecule is an image of the other molecule. And so we've been using, humans have been using this molecule for 6,000 years, and we've had the ability to see this molecule for about 30 years. And then right down here, then we're at 1 angstrom or 100 picometers or 0.1 nanometers. And now we have really single atoms. And this is an image type. This is one of our images that we take with our instruments here. And so each protrusion that you see there is an individual atom of silicon. Obviously, at the silicon surface. So I kind of indicated here, everything to the left is your classical world, and everything to your right here is the quantum world. Underneath, I've got some length scales of imaging techniques. So, from sort of human hair thickness up, we can see with our naked eyes. Then we have this regime here, optical microscopy, where it's actually red blood cells. And I think E. coli, I think that's sort of right at the limit of what we can see with an optical microscope. Scanning electron microscopes, these operate, scanning electron microscope, they operate very similar to optical microscope, but rather than sort of reflecting optical light, we're reflecting electrons. And then we have the regime of scanning probes. So this is scanning tunneling microscopy. That's the technique that we use. There's a related technique, atomic force microscopy. And the last one here, this is transmission electron microscopy. So this, the FinFET transistor, that's a transmission electron microscopy. Yeah, so we're going to talk sort of about down here in this quantum world, and obviously quantum effects dominate at these small length scales, but everything everything bigger, right, is still built out of these same individual building blocks. Although we don't sort of notice quantum effects at our length scales, they're still very much the reason for the properties of atoms and molecules and materials. Okay, so I wanted to start with a little sort of introduction to quantum mechanics. And I don't know how much maybe you've touched on it in chemistry and a little bit of physics. But I want to sort of touch on start with this to give you kind of the flavor, right, the sort of central quantumness of things. So this is J.J. Thomson, right? So he discovered the electron, and he proved in doing that the electron is a particle. But he measured, you probably do this in school, where you measure the charge to mass ratio and prove that this electron is a particle. And so he received the Nobel Prize in 1906 for proving that the electron is a particle. I added this at the end. This is not really part of what I want to talk about, but the electron itself, I've drawn it as like a big ball, right? But as far as we know, the electron has no size and no shape, right? So there's still people that are trying to measure, is there any shape to an electron? So, but really, as far as we know, electron, it has a mass. We know its value of its mass. We know the value of its charge. It's mass and charge. But, in some sense, you could think of it as being almost just a mathematical object, two numbers. But that's sort of slight diversion from what I want to talk about. So this next slide here, the last one was the electron as a particle. This slide is the electron is a wave. This is George Thomson. So that's the son of J.J. Thomson. So he fired electrons at crystals and saw diffraction patterns. And in doing so, he proved that electrons are waves. And they gave him the Nobel Prize for that in 1937. And so one proved the electron is a particle, the other one proved an electron is a wave. There's not much different, right? Those are completely different things, right? Particle and a wave, completely different things. They're both right? So electron is both a particle and a wave, and that is really there's really the crux of quantum mechanics in a way. We call it wave-particle duality. So they're both right, an electron is a particle and a wave at the same time. And I put this second bullet point in bold because really you have to say this to yourself, multiple times, because you're going to try and reason the waviness of electrons, but you can't, right? So nothing in everyday life behaves like this, right? Nothing in everyday life that you experience has wave-particle duality, and your intuition is completely useless. It just can't apply. So it's unavoidable. We try to rationalize it, but we can't. So that's why we have to do these experiments to really probe materials at these length scales. But this wave-particle duality is really a fundamental property of matter, right? So it's a fundamental property of electrons. It's a fundamental property of light, right? Photons. Photon of light is a particle, but light clearly has wave properties as well. Protons, neutrons, atoms, molecules, right? So they all have this wave-particle duality. It's just that as you get bigger and bigger, you start to lose. You don't notice so much the wave property anymore. And this is then kind of the canonical quantum experiment, right? So this kind of captures this idea of wave-particle duality. Probably you have done Young's double-slit experiment, where two slits, you shine light on it, you see diffraction pattern, interference pattern, and that tells you that that the light is a wave. So this also happens if you do it with electrons. We take a beam of electrons, we fire it at this pair of slits, and if they were particles, right, if this were sand or tennis balls or something like that that we were throwing two slits, then what you would expect to see is two piles of sand, or two spots where the tennis balls hit, right behind where these two slits are. But when we do the experiment, that's not what happens. We see the same interference pattern on the screen as you do with light. And that really proves that the electrons have these wave properties. So I'm going to show you a movie here, and this is the real experiment. So it's a pair of slits, and we're firing electrons at those two slits, and we fire them really one at a time. So you can see there's a spot here and a spot here, right? So the electrons are arriving one at a time, and this is the real time experiment. That's how slow the experiment was done. So they did really slow so they could be sure that only one electron is passing through the slit at any time. In a moment, it'll speed up, right? Because it takes a long time to accumulate. So it gets faster. It's going to get faster again later. And so what's happening here then is we're generating an electron, right? You can generate an electron if you heat a piece of metal, you can generate electrons. And the electron then is coming to this pair of slits, and then the electron, can pass through one slit or the other slit, and then it's going to arrive at the screen. And when it arrives on the screen, we detect. And so the first thing that you notice is that this already proves that an electron is a particle, right? We never see a half an electron arrive. We never see a blurry mass arrive, right? So you always, if you detect an electron, if you detect the electron, you always find that you get exactly one electron arrives. And when the experiment first started, you saw that the arrival pattern was more or less random. But as we collect more and more and more electrons, then you see that this interference pattern emerges. And so that really is the real that's the real experiment. And so what I've drawn here on the bottom, this is the we call it in quantum mechanics, we call it the wave function, the waviness of the particle. That's a wave function. And this is the wave function for this experiment. So classically, our naive picture is the electron passes through one slit or it passes through the other slit, and we should get a pile here and a pile here. But instead what happens is the electron, we don't know exactly what happens. Right? The electron comes towards the slit, it somehow passes through both slits, or there are various different kinds of language that we can put on top of this. One of them is that it passes through one slit in one universe and the other slit in the other universe, right? Like these ideas of multiple universes, they come from this experiment. But then if this were a waterway, so this diagram, I guess, you could think about this as dropping a stone into a pond, and you would see circular wavefronts coming out of the pond. And then the circular wavefronts, when they reach these two slits, then you would have two more circular wavefronts. The blue line is showing you where the water would be highest, and then in between the water would be lowest. And so on this side, where the two blue lines overlap, you're going to get constructive interference, so the wave height will be even higher, and then in between the wave height will be lower, right? And so if you take a slice through that, then you have this pattern of increasing and decreasing amplitude. And so this is the wave function, and you can basically think of this as being as a wave of probability. So that the wave function tells us what is the probability that we will find the electron in that space. And that's why you see that this sort of correlates. For any individual electron, we have no way of telling where it's going to arrive. They arrive randomly, but after we build up more and more and more, you can see that there's a much higher probability for the electrons to appear here than there is to appear here. So that's a wave particle duality, a double slit experiment, which kind of gives you that's really the sort of canonical experiment that tells you about wave particle duality. I started the presentation by saying that we use tunneling microscopy, so electron tunneling, scanning electron tunneling microscopy. And that's another consequence of this sort of waviness, this wave particle duality in quantum mechanics. And so I can illustrate that now with this slide. So the top, this is sort of on the left, this is the before picture, and on the right, it's the after picture. And so you can imagine if you had a ball and you had a hill, and if you roll the ball toward the hill, if you roll it just very softly, right, it'll reach the hill and it'll start to go up, but it doesn't have enough energy, so it won't go over. Instead, it's going to fall and roll back down. So that would correspond to this particle being reflected from this barrier. But then if you do it again and you roll the ball very fast, right, then you give it by rolling it fast, you're giving it more kinetic energy, and it has sufficient kinetic energy that it's going to rise up and go over the barrier and smoothly go down the other side. So that's the classical picture that we're all, that's our intuition. In quantum mechanics, there is a chance that if you take this ball and you roll it with insufficient energy to go over the barrier, that it still passes through. So this is what we call quantum tunneling. So I just roll this very slowly, approaches the barrier. Classically, you would expect it would just roll back. Quantum mechanically fine, it appears magically on the other side of the barrier. And it's a bit like what I said in the double slit experiment, right? We don't know what happens in the middle, right? By the way, if you try and look what happens in the middle, you destroy it. It doesn't work anymore. Right? If you try and see which slit it goes through, then it definitely passes through one slit or the other. So you only get the interference back if you don't look to see which one it went through. It's kind of the same here. So we can sort of fire the electron, and then we can look to see if it arrives on a screen on this side. And with some probability, quantum mechanically, it will. So I want to make that a bit more concrete in terms of what, the quantum tunneling, a bit more concrete in terms of what we do. And so first of all, I'm going to explain. I think you all studied the photoelectric effect, no? Okay. Okay. Well, I was assuming that you had studied the photoelectric effect, and so this is like the classical picture. And so this sample here is a piece of metal, and in the metal you have all of these energy levels. The energy levels go all the way to the top, but you only have a certain number of electrons in the metal. And so those electrons fill up to a certain level, and then it stops. So in the photo, so the diagram showing energy on the y-axis and distance on the x-axis. So this would be the surface of the metal. So if I want to get an electron out of that metal, what I can do, right? So I've illustrated just one. All this blue region is many, many electrons. So there's one electron that's sitting here with its highest energy. If I shine light on that, then I can, here you see this is a photon now, which is a photon is also a particle in a wave. The photon gives all of its energy to this electron. So and if that amount of energy is greater than this work function, this is called the work function, this difference, then the electron will be photoexcited, and then it also has kinetic energy. So then it will leave the crystal. And so that's like the first, it's a quantum picture of it. It's that sort of classical process where we give the particle enough energy to overcome the barrier. But if instead now I want to describe the quantum tunneling version of that. So we take the same electron, think about it at this highest level, then this electron has this wave function, and if I bring in now another metal, right, very close, so this wave function decays quite rapidly. So the distance here has to be about 0.5 nanometer, about 5 angstroms or so. But then you can see if I had another metal, the two wave functions overlap. And this is the basis for quantum tunneling. Right? But nothing is going to happen here. Right? So there's like this box here is vacuum. Right? So you could eject the electron by taking it up over this barrier. But we're not doing that in quantum tunneling. But nothing's going to happen here because there's an electron on this side and there's an electron on that side, and everything's sort of happening the way it is. So what we do is we apply a small voltage between the two. And this offsets those two energies. And so now I said that there's energy levels all the way up, right? So there's even energy levels as you go higher up that just don't have any electrons in them. And so there's another wave function here that describes this state where the electron could be, but there isn't currently an electron there. And now if you look at this pattern, right, this looks very much like that interference pattern of arrival at the screen, right? And I said that wave function describes the probability that we'll find the electron. So now if we look for the electron, there's a probability that we'll find the electron over here. And so that's the basis of quantum tunneling. If the electron does appear over here, then we have a bias voltage, and these are connected by a wire, and so there'll be a current that'll flow through. So you know from your experience, if you take a battery with two wires, no current flows until you touch the batteries, touch the wires together. But in tunneling, if you get them close enough, half a nanometer or so, then you get this tunneling current. That's the basis of our microscope. So we make this as a sharp metal tip. So this is the last atoms on a sharp pointy piece of metal. And then this is the atoms of the surface we want to measure. We apply a bias voltage. This establishes a tunneling current, and we can then scan the tip over the surface. And we use a feedback loop in a computer to change the tip height so that the magnitude of that current doesn't change. And so then if we plot the voltage that we need to move this tip up and down, then we map out the surface like so. I'm going to show you an image of a surface, but first I just need to explain what the crystal is that we're looking at. This is a silicon crystal. Every atom in the silicon crystal is bonded to 4 other silicon atoms. And that's the crystal structure. If we make a surface by cutting through the top, right, each one of these atoms at the surface used to be bonded to an atom that was above it. But now it's no longer there because we've cut the crystal. But this is very unstable because we have these broken bonds that would be sticking upwards. And so what happens is these atoms come together to form rows of paired atoms, which we call diamonds. And here's then an STM image of this silicon surface. And what you're seeing are these rows of paired silicon atoms. So on the left-hand side, you see each one of these kind of, these sort of baked bean-like protrusions. That's a pair. We're not seeing individual atoms, we're seeing pairs of silicon atoms. And then because the bonding in the crystal, if you sort of look at this closely enough, you can see that the bonds rotate by 90 degrees as you go down each atomic plane. So on the bottom here, this is one atomic step that you see running along the middle of the image. And then the diamond rows run in the perpendicular direction on the lower terrace. So I'm probably going through this quite fast now. I could stop for questions if you like, or I can keep going and have a. Okay, I'll keep going. Right. So we can, the bonding itself is also a quantum process. Right. We talked about the wave function. The wave function is the solution to the Schrodinger equation. And the Schrodinger equation, this little thing, this H with a hat over the top, it hides. This is the second order differential equation. So this hides. It's basically d squared by dx squared inside this H term. But the side here, this is the wave function. Right. So if we think about, I want to talk about that bonding that we saw, the two silicon atoms coming together to form a bond. Right. So if we think about the electron in that bond, so we solve this Schrodinger equation, and we get this wave function. So it's electron in its wave function, and this is on one of the silicon atoms. Then we have the other silicon atom, right? So it also has this wave function. And so what happens when we bring these two atoms together, right? So we take the wave function, this psi, and we add them together, right? And there's another complication that no one actually knows what the wave function is. So this wave function psi, we don't know what it is, and it's complex valued in general. So in order to turn it into the probability that I mentioned, we have to take the modulus squared of the wave function. So this then is the modulus squared of the addition of the wave function on the two atoms. and we get this overall wave function now. And so that's what we were imaging in the previous image. That sort of big beam protrusion was this charge density that exists between the two atoms. So that's the chemical. It's also the chemical bond. Right? So without quantum mechanics, we can't describe chemistry. We can't describe bonding. But bonding comes from quantum mechanics. But we can also subtract the two wave functions. Right. So if we take this wave function and we subtract this one, right? So you can think about turning this one upside down. So that would give you a kind of like a sine wave. But then we need to take the modulus squared. So you take the modulus squared of that subtraction wave function, and you get this new wave function here that has a nodal plane in the middle. So I've drawn them like that because the bonding combination it is lower. The system gains energy when the two wave functions overlap to form this bonding orbital. The system gains some energy. The anti-bonding one is higher in energy. So this is the anti-bonding. So the two electrons, they go into this bonding orbital. But there's nevertheless this state up here that exists, but it doesn't have any electrons in it. But we can also probe this state with our microscope. And it depends on the polarity of the voltage that we apply to our tunnel junction. So when we have a negative sample bias, we tunnel electrons from the sample, so from this bonding orbital between the two atoms, the electrons come out into the tip. But if we reverse the polarity, so now we change to plus 2 volt sample bias, we can now inject electrons from the tip into the sample, and we image this anti-bonding orbital. And so you can see the anti-bonding orbital, we resolve the two atoms separate. I think I was maybe slightly ambitious with how much I thought I would get through. I have a few more slides. Where's my cursor? But maybe I will just skip to this one. So this is the data. I showed you some of this data on the title slide. So by now you can grasp what this image is. This is the silicon surface. So these rows that you see running diagonally through the image, these are our rows of paired silicon atoms. Right. So we're a bit more zoomed out. So you can't quite see the little individual baked beam protrusions quite as well, but you can see the rows. So these are the rows of paired silicon atoms. And then what we've done is taken this the silicon wafer, and we took it to the University of Surrey, and we fired a high-energy beam of bismuth atoms. So we basically implanted bismuth atoms into this crystal, and the bismuth atoms are underneath the surface. So you can think about now this bulk silicon crystal, and underneath the surface, every now and then, there's a bismuth atom. And we can see the bismuth atoms. So that circle these large, very large, right? So some of these are as wide as kind of 10, I haven't put a scale bar on this, but the distance between the rows is roughly 1 nanometer. So some of these are kind of as large as 10 nanometers across. And these are the locations of these of the bismuth atoms. And we know that because we can model the properties. This is a theoretical model of what wave function that these individual defects might fall. So essentially, if you imagine in the center of this cube-like shape here, you have your bismuth atom, and for many reasons that we don't have time to go into, that bismuth atom produces this very large electronic wave function. So there are individual electrons bound up in the bonds between silicon atoms. There's also one electron surrounding each of the bismuth that's in this very large cube-shaped wave function. And because this wave function is so big, it reaches, provided our, if this cube is 10 nanometers across, right? So provided our bismuth is less than 5 nanometers underneath the surface, then this wave function extends up to the surface, and we can image that wave function. And so that's what we published this last year. And it's a collaboration. There's a theorist, Michael Flatte at the University of Iowa. He and his students have done this theoretical modeling for us, which we had good suspicions about what these wave functions were, but in order to show it, you really need to do the detailed theory. Yeah. And why are these interesting? So this is a diagram that I was shown at the start of my PhD in 2000. And this is a proposal for a quantum computer. And this quantum computer relies on positioning individual atoms into silicon crystal. The original proposal, these are phosphorus atoms. So this is the blue box here is a piece of silicon. The red circle represents a single phosphorus atom, and you can see there's another single phosphorus atom that's 20 nanometers away. And it's the spin, right? I guess you haven't its spin probably, but the nucleus has a spin, and the spin can be either spin up or spin down, and that allows this to function as a quantum bit or a qubit. But the way, to make a computer, you don't just have to have bits, but the bits talk to each other. And so the way they talk to each other in this proposal is by these electron states. So this red circle that surrounds each of the atoms, it's just such a wave function. So one of the things that we're trying to do, not just here at UCL, but there's quite a few groups around the world, is to develop this technology into a workable quantum computer. And if you've heard of quantum computing in the news, and these are you might have heard like from Google and other companies that have already 100 qubit quantum computers and things like that. But the individual qubits that they're using in those devices, they sort of manufacture them, and it requires a lot of tuning, right? So as these devices get bigger and bigger and bigger, each one of their qubits, they have many different voltages that they need to tune just to become a qubit. So with our qubits, if we're able to position individual atoms into a silicon crystal, where the individual atoms themselves are all identical, so we don't have that problem. Our problem is that building at the scale of single atoms is really quite challenging. But nevertheless, this is what we're working on. So with that, I had a couple of minutes over time, but I'll stop. So that was hopefully a brief introduction to the quantum world. So electrons, photons, atoms, molecules, they all have this wave-particle duality. Wave-particle duality, there's no way you can understand it with your intuition, but it's nevertheless one of the most fundamental aspects of the universe, that we live in. And it explains a great many things. And yeah, so we're exploring this quantum world, doing careful experimentation and comparing that with physical and mathematical modeling. And of course, I guess I would say my main motivation is just the knowledge, right? Just learning about these systems, learning how to develop more and more accurate theories to describe these systems. But there are also potential technological outcomes. We could potentially use what we're learning to build devices like the potential future solid-state quantum computer.